In the winter of 1949, a 25-year-old student named Johan Halton traveled to a remote Alaskan village. He hiked to a mass grave, hacked through thick permafrost, and extracted human lungs from the frozen earth. The people buried in that ice were killed by the 1918 Spanish flu. Halton was hunting for the specific biological code of the virus that caused the pandemic. He placed the tissue samples in a specialized solution and rushed them back to a laboratory. But his mission hit a dead end. The virology tools of the 1940s weren't sophisticated enough to isolate or revive a dormant pathogen. Nature had archived a mass killer in the permafrost, effectively removing it from the human environment. But Halton's mission signaled a shift. Human curiosity was now actively digging back into that archive. Halton waited 47 years for technology to catch up. In 1997, at 72 years old, he returned to that exact same Alaskan permafrost. He found a perfectly preserved victim and successfully extracted new lung samples. He sent those samples to military researchers. By 2005, using those frozen fragments, scientists achieved the unthinkable. They successfully reactivated the 1918 Spanish flu virus in a high-security lab. Which brings us to an uncomfortable question. Why are highly trained virologists going out of their way to resurrect the deadliest pathogens in human history? They aren't doing it to play God. They are reconstructing these ghosts of the past to understand how they function. Scientists need to map their weaknesses now, because we may soon lose the luxury of studying them in a controlled environment. The controlled environment of the lab is becoming the exception. In 2016, a heat wave shattered a 70-year temperature record in Siberia, triggering a massive melt of the permafrost. Deep within that ice was the corpse of a reindeer that had been frozen for 7 decades. As the surrounding ice turned to water, dormant anthrax bacteria inside the animal thawed out and drifted directly into the air. The outbreak was swift. It killed a young boy, sent 115 people to the hospital, and wiped out more than 2,300 reindeer in the surrounding area. We no longer need researchers to dig up these threats. Rising global temperatures are unearthing microscopic killers that modern human biology hasn't encountered in centuries. To see why these ancient viruses are so dangerous, we have to look at the cellular interface. A virus uses its spike proteins to mimic the signals our cells expect, tricking the cell's receptors into allowing the invader to dock and offload its genetic code. Fortunately, our immune system has a defense mechanism. Specialized defenders called T cells carry an immunological memory diary, a biological logbook of past infections. When a familiar virus enters the body, the T cells check their records, recognize the threat, and destroy it. The problem with ancient permafrost viruses is that they are entirely absent from that diary. Because we haven't faced them in millennia, our T cells scan the invader and find absolutely zero record of it. The virus slips right past our biological security. Once the body realizes it is being overrun by an unknown enemy, it panics. It triggers a cytokine storm, a massive release of chemical signals that sends the immune system into overdrive. Blinded and desperate, our own defensive cells start attacking and destroying healthy tissue. Because our bodies lack the historical data to mount a targeted defense, an ancient infection effectively turns our own immune system into a lethal weapon against us. We've seen how sudden environmental shifts can unleash biological chaos. In September 1993, a massive earthquake devastated Latur, India, reducing entire villages to rubble. As the earth shifted and buildings failed, the local ecology was forced into a collision course with the survivors. Plague-carrying rats were driven out of the forest, seeking shelter and food within the grain stores of the village. As the outbreak spread to the city of Surat, the bacteria mutated into the airborne pneumonic plague. Panic swept the streets. Within 48 hours, 300,000 people fled the city, overwhelming transportation networks and carrying the risk of infection with them. An unearthed pathogen only takes a single localized outbreak to spark a domino effect, shattering supply chains, emptying hospitals, and triggering widespread social collapse. The threat is accelerating. Recently, researchers have successfully revived dormant viruses that had been frozen in the earth for over 30,000 years. While a pathogen emerging in remote Siberia might feel distant, it has a direct flight path to our doorstep. As the ice melts, these ancient viruses are positioned to infect millions of migratory birds that pass through the Arctic. Physical distance offers no protection. A single infected flock can transport an ancient plague from the thawing tundra straight into the airspace of major metropolitan cities. If that happens tomorrow, we are entirely unprepared. Globally, we lack sufficient biosafety level 4 laboratories to study these threats, and we have almost no dedicated surveillance networks monitoring the permafrost for ancient pathogens. Worse still, our bureaucratic defenses are relics. Many nations are relying on outdated legislation, like India leaning on an epidemic act written in 1897 to manage complex 21st century biological crises. We need immediate, massive investments in rapid mRNA vaccine technology, capable of responding in weeks. We have to secure our medical supply chains and modernize our epidemic laws before the next crisis hits. Nature will not issue a warning before the next ice-locked pathogen finally awakens. We have to rebuild our global defenses right now, before the global thaw is complete.